Welcome to the second lecture of Introduction to Electrical Circuits. Last lecture we have seen some definitions, in particular definitions of the physical quantities that are used to describe circuit, that is current, voltage and power, as well as the sign convention that we use to describe the behavior of a two-terminal component. Today we are introducing the electrical equations that describe the behavior of the circuit. Like in every physical theory, we have two kinds of electrical equations. The equations of interconnections, also known as topological equations, that describe the behavior of many components interconnected together. For us in electric circuits, these equations are the Kirchhoff equations. The second kind of equations are constitutive equations. Or component equations that are links between the voltage and the current associated to a specific component. So they are equations of the form V equals V of I and T, or I equals I of V and T. The first equations that we are going to introduce are the Kirchhoff's equations. But before doing that, I want to introduce a few key concepts of topology. In particular, I want to define the concept of branch, For branch, we consider any component of the circuit. The concept of node. For node, we consider the interconnection point among two or more branches. Then I want to introduce the concept of loop. A loop is a closed path made of branches. And finally, the concept of mesh as a loop that does not contain any loop inside. In order to explain these concepts, let's make a reference to a generic circuit. This circuit contains four components. Let's call them A, B, C, and D. So the number of branches is 4. Then we have 1, 2, and 3 nodes. Let's call them 1, 2, and 3. Then, if we consider loops, we have one loop made by the components A, B, and C, one loop made of by the components C and D, and finally one outer loop made by the component A, B, and D. So the number of loops is 3. Now, if we want to consider the number of meshes, we have to identify among these loops which ones does not contain any inner loop. So, for sure, the first two loops that we have mentioned, so the loop made by A, B, and C, and the loop made by C and D, for sure does not contain any inner loop. So these two can be also considered as a mesh. While the outer loop made by A, B, and D contains in the middle the component C. So inside the outer loop we may see other inner loops. So the outer loop is not considered as a mesh. So the number of meshes in this circuit is 2. In other words, every mesh is a loop, but not all loops are considered as a mesh. I have introduced these topological concepts because we always have to distinguish between the topological representation of a circuit and its graphical representation. For instance, we may say that we have only one topological description of a specific circuit, but we may have many different graphical representations. For example, this second graphical representation of the circuit is different from the previous one, but from a topological point of view, we are considering exactly the same circuit, because in both cases, for example, the component D is connected between the nodes 2 and 3. This consideration comes after the consideration that we have done before, when we said that we don't have to consider any geometrical information from the picture of a circuit. So a component can be long or short, the connections can be large or not, but these concepts are not affecting the behavior of the circuit, because all geometric information is already considered when we draw the box of the component, because all phenomena are constrained inside the box. Let's start with the definition of Kirchhoff's current law. Of course, it involves the currents in a circuit. So let's draw the currents in each component according to an arbitrary direction that we choose to study that component. For example, IA going up, IB going left, IC going up, ID going right, and finally IE going down. Kirchhoff's current law states that at any instant of time, the algebraic sum of the currents flowing through any closed and oriented surface is 0. This definition requires some clarifications. First of all, I want to highlight what is a closed and oriented surface. Closed and oriented surface is what is usually called Gaussian surface. A Gaussian surface is the boundary of a volume, so you can consider a generic volume, take the boundary of the volume, so the skin of that volume, and for this specific surface you can define an arbitrary orientation, so you can define a unit vector pointed outwards or inwards. Let's consider, for example, a generic Gaussian surface that is touching the circuit that we have here. For example, this one. And let's assign to this surface an arbitrary orientation. For example, we use the unit vector that is pointing outwards. Now, what we have to do, according to the definition, is to consider the currents flowing through this surface. This means that we have to identify the currents that are crossing this surface. In particular, we have an intersection between the circuit and the surface in this point, and this point here. So actually we have identified 3 currents that are flowing through the surface. For these currents, we have to make the algebraic sum. Algebraic sum means that we have to consider for each current the correct sign. In particular, we have to infer a convention for the currents that are crossing the surface. For example, we consider the currents that are crossing the surface with the same direction of the orientation of the surface as positive currents, while the currents that are with the opposite direction with respect to the unit vector are taken with the minus sign. In our case, the unit vector is pointing outwards, so all currents that are flowing outside the surface are taken with the plus sign. All currents that are flowing inside the closed surface are taken with the minus sign. So in our case, we have the current IB that is flowing out as well as the current E, while the current C is flowing inside. So B and E are taken with the plus sign, while C is taken with the minus sign. IB minus IC plus IE. And finally, we have to say that this sum is 0. This is true at any time instant. So this is true for every time that we consider this equation. For example, we can make another surface. This time we can take the surface that is surrounding this node here. In this specific case, we have 3 intersections in this point, and this point. The currents are not readily available right now, but if we consider, for example, the component A, we know that the current is flowing up in this case. This means that it's flowing down, it's flowing up also before the component. And this is the current A as well. And this is current IA. The same happens for the component C. The current is flowing through the component C from the bottom to the top, and so this is current C as well. Finally, for the element E, the current is flowing down, and so this is current E, and this is current E as well. Now that we have projected the currents close to the surface that we are considering, we can write the algebraic sum for these currents. We consider again an outward pointing unit vector. So the currents that are flowing out are taken with the plus sign. The currents that are flowing inside the surface are taken with the minus sign. And so we have that IA plus IC minus IE equals 0 for any time instant. Let's make some comments regarding the Kirchhoff's current law. First of all, we may write in short that Kirchhoff's current law is the sum of the currents IK with a specific coefficient, let's call this coefficient alpha, with the subscript k that goes from 1 to the number of branches, and this sum is 0, where the coefficient alpha can be +1, -1, or 0, according to the fact that the current is flowing through the surface according to the direction of the unit vector. So alpha k is 1 if ik is flowing through the surface in accordance with the unit vector. It is minus 1 if ik is not in accordance with n. Alpha k is 0 if ik is not crossing the surface. For example, if we go back to our first Kirchhoff current law, we considered only the currents IB, IC, and IE, while we haven't considered the current IA, since IA is not crossing the surface. In other words, the coefficient for IA was 0. The second comment is that the Kirchhoff current law is a homogeneous equation. This means that the right-hand side is 0. But if we consider, for example, the first equations that we have written before, this means that if we change all signs for the current, the result is still 0. So this is a way to say that it doesn't matter the orientation. So the orientation of n is arbitrary. And also the convention that we used to get the plus and minus sign is arbitrary as well. In other words, we may consider that the currents that are flowing inside the closed surface are taken with the plus sign, and the currents that are flowing outside are taken with the minus sign. All in all, the final equation for Kirchhoff current law doesn't change its meaning. Third comment. Let's consider, for example, the second equations of Kirchhoff current law that we have written. And let's move, for example, the current IE to the right-hand side. In this case, we have that IA plus IC equals IE. This is not just to play with the currents and with the formula, but let's see if we can make some considerations about the inside of this representation of Kirchhoff current law. If we consider, for example, the surface that we are using for this Kirchhoff current law, we can see that the current IE is flowing towards the surface, while the currents IA and IC are flowing outside. So, what we said with the new formulation of Kirchhoff current law is that the sum of the currents that are flowing in equals the sum of the currents that are flowing out. It's a sort of current conservation. Last comment. Usually, the Kirchhoff current law is applied to nodes. I mean that usually we apply the Kirchhoff current law to closed surfaces that are similar to the red one and not to the green one, even if in some cases being more flexible with the definition of the surface may help us in reducing the number of calculations. For example, applying the Kirchhoff current law to the green closed surface may help us in solving the circuit without calculating ID that does not appear in the Kirchhoff current law. Let's now refer to the same circuit as before, but now we want to define the Kirchhoff's voltage law. So the first thing that we have to do is to define the voltages in this circuit. Again, we will assign an arbitrary direction for the voltages. For example, VA is pointing up, VB is pointing to the left, VC is pointing up, VD is pointing right, and finally VE is pointing up. This orientation is arbitrary and it is not related to the orientation of the current. In order to simplify how we define the Kirchhoff voltage law, let's also give a name to nodes. So this is node 1, node 2, node 3, and node 4. Kirchhoff voltage law states that at any time instant, the algebraic sum of the voltages along any oriented loop is 0. This time we define an oriented loop as a closed path. For example, the path that is passing through the component A, B, and C. But this path must be oriented. So we have to define if we follow the path according to the clockwise or counterclockwise orientation. For example, let's consider this with the clockwise orientation. So, in order to write down the Kirchhoff voltage law, we have to define the voltages along this path. In this case, in this path we find VA, VB, and VC. Now, these voltages must be summed up with the correct sign. In fact, we said that we have to calculate the algebraic sum. The algebraic sum means that we have to assign a plus to the voltage that is found through the path according to the direction that we have assigned to the loop, or we use the minus sign if the voltage is with the opposite direction with respect to the orientation of the path. So, let's suppose, for example, that we are starting from node 4 and we follow the path clockwise. So, if we move from node 4 to node 1, we found out the voltage VA, and VA is following our orientation, so VA is taken with the plus sign. Once we arrive to node 1, we can move on and go to node 2. In this case, we find the voltage VB, but VB is oriented with the opposite direction, and so VB is taken with the minus sign. Finally, if we move from node 2 to node 4, we find the voltage VC, and also in this case, the direction of VC is opposite with respect to the orientation of the path. And so, also in this case, we use the minus sign. And this sum is 0 at any time instant. We may select, for example, another loop. Let's take, for example, the outermost loop. So, the one made by A, B, D, and E. And just to change, for in this case, the orientation, we can use the counterclockwise orientation. Now, let's start again from node 4 and let's move according to the orientation of the path. So we move from node 4 to node 3 and we find the voltage VE, that is in accordance with our orientation. So VE has the plus sign. Then from node 3 we move to node 2 and we find the voltage VD that has the opposite orientation with respect to the path, and so we say that VD has a minus sign. From node 2 to node 1 we find the voltage VB. This time it has the positive orientation, so plus VB. And finally we move from node 1 and we close the loop going to node 4. We find VA. VA is again with the opposite orientation with respect to the path, and so we take VA with a minus sign. And this sum is 0 at any time instant. Let's introduce also for Kirchhoff's voltage law some comments. The first one is that we can write the Kirchhoff voltage law as the sum of the voltages of all branches. So for K that goes from 1 to the number of branches B, and this voltage is taken with a specific coefficient. Let's call this beta K, and this sum is 0 for every time instant, where beta K is a coefficient that can have the value plus 1, minus 1 or 0. It is plus 1 if Vk is oriented in accordance with the loop, minus 1 if Vk is not oriented in accordance with the loop, or is 0 if Vk does not belong to the loop. The second comment is similar to what we said for Kirchhoff's current law. KVL is a homogeneous equation. So, the orientation of the loop is arbitrary, and the convention for the plus minus 1 signs is arbitrary as well. For the third comment, I repeated here the circuit because we need it for the consideration. We wrote before that VA minus VB minus VC is 0, but let's move the voltages with the negative sign to the right hand side. In this case we have that VA equals VC plus VB. We may explain this version of Kirchhoff voltage law in this way. Suppose that we are in node 4. In node 4 we have the potential of node 4. And we want to move from the potential of node 4 to the potential of node 1. In this case, we can make a single jump using the voltage VA. So VA is the voltage that allows us to increase the potential of node 4 to the potential of node 1. Or we can make two steps. Starting from the potential of node 4, we jump to the potential of node 2 using VC, and then we jump to the potential of node 1 using VB. So we may represent the potential jump between node 4 and node 1 with VA on one side or VC plus VB on the other side. So we may see the Kirchhoff voltage law as a jump of potentials. For the last consideration, we refer again to the original circuit And we can state that usually Kirchhoff's voltage law is applied to meshes, so to loops that does not contain inside any other loop. So it is more likely to see Kirchhoff voltage law applied to the red path and then to the green path.